Doncs ara entrem a un terreny on la innovació no només tracta de fer models més grans o més ràpids, sinó que de repensar l'arquitectura mateixa dels sistemes intel·ligents i també una mica lligat a la pregunta que feien de tema de sostenibilitat i l'energia que necessitem per a aquestes grans tecnologies. Doncs la computació neuromòrfica, també coneguda com a neurocomputació, es basa en una transformació radical del processament de les dades, proposant una alternativa a l'arquitectura computacional clàssica de von Neumann, on processament i memòria coexisteixen i es redueixen les pèrdues d'energia i latència. Però com portar aquest paradigma emergent a aplicacions reals, robustes i escalables? Quins reptes de disseny, de fiabilitat, hardware especialitzat i integració amb la IA clàssica cal resoldre? Aquestes són una de les preguntes que en fem amb aquest framework. És un honor, doncs, presentar el nostre ponent per a aquesta sessió, Mario Lanza, professor a la National University of Singapur i doctor d'Enginyeria Electrònica per a la Universitat Autònoma de Barcelona. La seva trajectòria com a investigador l'ha dut a terme a Stanford i ha liderat grups de recerca a les universitats de la Xina, com també d'Aràbia Saudita. La seva recerca actual es centra en el desenvolupament de hardware de baix consum per, entre altres, usar-lo per a aplicacions d'intel·ligència artificial. I en aquesta ponència ens presentarà els conceptes clau de la neurocomputació i les claus dels dispositius neuromòrfics que poden esdevenir disruptius per a una computació més eficient, tant des del punt de vista de potència de càlcul com d'eficiència energètica. Doncs, Mario, quan vulguis.
Thank you very much for the nice introduction, and thank you very much to the organizers for inviting me to give this presentation in my hometown. It's a great pleasure. Thank you, everybody, for being here to listen in. I'm going to be talking today about neuromorphic computing. It's a kind of new computing paradigm in between of what we have now, the CMOS technology, and what we may have in the future, the quantum computing. And I would like to start this presentation with this picture. It's the picture of the first general-purpose electronic computer, the ENIAC, developed at the University of Pennsylvania. And when I show this picture to my students and my postdoctoral fellows at the National University of Singapore, they find it funny, obsolete, archaic, because we have all already got used to have the power in our hands. This machine was capable of making 5,000 zooms and 350 multiplications per second, and it was revolutionary on that time, but right now, this is obsolete. As you can see, this computer was huge. It occupied one entire room, and it needed to be programmed through these cables connecting several vacuum tubes, and this was very laborious. And right now, as I mentioned, it looks a little bit even funny. However, I think we have been listening so far several speeches saying what we can do with artificial intelligence, but I am here to warn about the problems that we may have also with artificial intelligence, because even if in our daily life we only interact with this, when we put artificial intelligence here, we are going back to computers and systems that look like a room or like a building, and that even more important, that consume huge amounts of energy, that are fabricated in very unique laboratories, just a couple of laboratories in the world, and that have all the control. So I'm going to be talking about the problems of AI, about the hardware that implements AI, and about what can be done to tackle those problems. And this is the outline that I will follow. First, I will describe from a very historical perspective, because we have to talk about physical mechanisms to understand what is the root of the problem. Second, I'm going to explain how is the hardware that right now implements artificial intelligence. And third, I will show you a new electronic device that we have developed in my laboratory at the National University of Singapore that we believe it can tackle several of these issues. So we have, in order to understand really how electronic data is processed, we have to go back to the very beginning, to 1825, when it was developed the Ohm's law, which describes how charge carriers are moving in a solid, and in 1845, when the Kirchhoff law explained how charge carriers move in a circuit. Around that time, also people started to propose some kind of algebra called Boolean algebra based on two different states, zeros and ones. And by making several types of operations, one could develop circuits that can implement some more sophisticated operations. But this was just an abstract representation on a paper. There was no hardware capable to do that on that time. A few years later, Edison discovered the thermionic emission, and Fleming invented the vacuum tubes. And the vacuum tubes are formed by two electrodes. When a voltage is applied between the electrodes and reaches a threshold value, charge carriers can move from one electrode to another. This is placed in a vacuum because otherwise these charge carriers will interact with the oxygen and therefore they will be scattered. But this is a voltage control switch. And the switch was found to be ideal to implement Boolean algebra because it also has two states. And around 1937, a PhD student from MIT called Shannon developed the first circuits, real circuits, capable of implementing Boolean algebra. You can see here, these funny symbols represent the vacuum tubes. And apart from this, you have some resistors and diodes that are used to condition the signal. But what you see here is exactly the same of this, the physical representation. And it looks like this, just to make one bit full adder circuit, huge. Luckily, a few years later, these two gentlemen developed the metal oxide semiconductor field effect transistor, which is basically the same, a voltage control switch, but in this case, it's much smaller. It consists of a piece of silicon. When we apply an electrical field between these two electrodes, a conductive channel with charge carriers from the semiconductor can be formed here. And when we apply also bias here, you can drive current from one electrode to the other. The physical principle was the same, a voltage control switch. And with this, we managed to keep up miniaturizing the size of these switches, and this allows us to put more switches in the same space and perform more sophisticated operations. Here you can see, for example, how it looks exactly the same circuit I showed you before, but with MOSFETs, and this is the hardware implementation in a microchip. Much smaller, and from there, I think the rest of the story, all of you already know and you are familiar with it. After that, in 1971, the first central processing unit, or CPU, was invented by Intel. Here we have a unit that makes a lot of mathematical operations and a memory unit that stores the data. And with this fundamental principle, we managed to develop all kinds of electronic products that surround us. Calculators, microwaves, televisions, smartphones, advanced medical equipment, etc. Until 3 years ago, we discovered artificial intelligence, let's say massively. We witnessed the release of ChatGPT by OpenAI, which is a large language model that is able to interact with us, give us high-quality answers to very complex questions. And this is already amazing. I think here we can say the genie is already out of the lamp. This is the magic that we were looking for. However, implementing this artificial intelligence with these MOSFET transistors, with these voltage control switches that were ideal for Boolean algebra, it turns out to consume a lot of energy. And by 2030, we are expecting the energy consumption of electronic products mainly empowered by AI, will reach around 20% of the global demand, which is a lot of cost of money, and it's a lot of consumption of natural resources. Moreover, there is another big issue, as I mentioned at the beginning. Very few companies are able to fabricate these systems, which is extremely dangerous. So 20 years ago, when I was a PhD student, there were more than 20 companies in the world that could fabricate state-of-the-art MOSFET transistors. In Europe, we had several. It was fantastic. They sent us the most advanced samples. We analyzed them here in the Autonomous University of Barcelona, and we had very good results. Now, they cannot fabricate these transistors anymore. It has become extremely complex and expensive. And there are only two companies. One of them is TSMC, which produces 90% of the world production of advanced logic nodes from the 3-nanometer node and even more advanced, and Samsung, which produces less. So we need a solution. Even if we are happy with our AI, we are happy with the things that it can do, we are happy with ChatGPT, in the long term, we really need a solution for this. This is why companies are investing a lot on quantum computing. But quantum computing is something very difficult to understand, very counterintuitive, that proposes massive challenges. I'm going to propose something at a shorter time that is already being investigated by companies like Intel, like IBM, and several university groups. To understand the solution that we want to propose, first, we need to understand how artificial intelligence processes the information and the data. And I'm going to do it here with a typical example, which is an artificial neural network that recognizes images. Basically, the piece of information is the image, and it is divided in several blocks, in this case, the pixels. Each pixel contains an information which is codified with a physical magnitude, in this case, constant voltage. And we have a neural network that has a number of inputs equal to these small units, equal to the number of pixels of the image. So we codify the black, the gray, the white colors in a specific voltage, and we input it here. We have some internal memory nodes, and we have some outputs. The outputs are the classes. If we are going to recognize handwritten digits, let's say from 10 classes, from 0 to 9, then we will have 9 outputs. We are going to recognize not a few images, but the training data set for this neural network is around 50,000. Okay, so how it works is the following. The value that we input is multiplied by a number that we call weight. And then this happens for every input, and the results are sent to each one of the nodes, which make a sum, multiplication and sum. This is done several times until at the end we expect the correct output is activated. So how is this learning happening? How is this intelligence happening here? The learning is the process to adjust the value of the weights so that the right output is activated for each specific image. That's the learning characteristic. So adjusting the weights is the critical characteristic here. Let's analyze this a little bit at a smaller scale. Okay? I take here just one neural network. It's a unit, a building block called perceptron, that has 4 inputs. You can see each input is multiplied by one number. Then we have a sum. So basically what you have here is a small vector matrix multiplication. It's a mathematical operation. And then here we have an activation function that makes one comparison, which is normally, typically, these are the ones that are employed in state-of-the-art AI systems. Okay, so if you want to do this with traditional computers, we have a problem, which is, you remember that I mentioned that the computers have a unit that makes all the mathematical operations, and they have another unit which is the memory, where the data is stored. Here, there is a lot of data transfer. Data transfer slows down the computation and consumes a lot of energy, up to 60% in some cases. This is what many people call the von Neumann bottleneck, because this kind of architecture for computing is called the von Neumann architecture. So, as you have seen in the previous talk, the state-of-the-art systems are using mainly graphic processing units, because this kind of cards, what they do is they have several cores, and they can have several units to compute. Let's say they make this in parallel and improve a lot the performance. But the bottleneck is still there. They didn't solve the problem. So there are several solutions that are being proposed. This is one possibility. It has been proposed that we can use an array of memory nodes. We can do the multiplications. If we input some current, we can do the multiplication by Ohm law and the sum by Kirchhoff law in the memory. This is what some people call in-memory computing. And it's much more efficient because you don't need to move the data. The challenge is to achieve these memory nodes, multiple memory levels, and that can be reached in a linear way. So if we try to do this with the flagship memories that we have in the market, SRAM, DRAM, or flash memory, they don't do this. And therefore, the performance that we have achieved is not ideal. Okay? People is using SRAM cells that look like this, but SRAM cell is a volatile memory. It's not what we want here. And here you can see a representation of one circuit that makes this kind of mathematical function built with MOSFET transistors. Okay? You still need several transistors. And this is just a very simplified circuit. But there is another way to compute the information, which is trying to mimic what the human brain does. The human brain is formed by hundreds of millions of neurons that are connected by trillions of synapses. And these neurons produce some bioelectronic spikes. They are not constant over time. They are just around 50 millivolts, and they are not high frequency, but they are relatively fast. So some people have started to work in the direction of building spiking neural networks. They are the most energy-efficient neural networks. And in this case, the information is codified a little bit differently. Now, we don't codify with a constant voltage, but we codify the information of the pixels of the image, let's say, with the frequency of the spikes that are produced. So based on this, there is also a process of adjusting weights, and the memory nodes that are here, now they don't do only sums, because this is a kind of asynchronous system. What they do is a behavior called leaky integrate and fire. So let me show you this with a little bit more detail. Basically, you have this neuron where you input some data with different codification, with different frequency in the spikes, and then the potential of the neuron starts to increase as the spikes arrive. If the spikes stop arriving, the potential goes down. If more spikes arrive, the potential keeps going up until a threshold value is reached, and then the output generates one of these peaks. Okay? It's a very simplified explanation. There are several models for electronic neurons. You can see here the one I mentioned, leaky integrate and fire. There is the adaptive leaf. There is the stochastic model, etc. There are several others. What is the key problem? The key problem is that to implement one of these dynamic functions with the voltage control switch, which is the MOSFET transistor, you need to implement large circuits. The transistor, the physical mechanism of the transistor with this channel generated when I apply electrical field cannot mimic that dynamic behavior. And therefore, several research groups, this is a work from a colleague in ETH Zurich, Professor Giacomo Indiveri, and many other colleagues, they have proposed. And you can see what is the size of one neuron, 8,100 micrometers square. Okay? This is big for one neuron. Now think you have a neural network with millions of neurons. So basically, the solutions that are doing some companies, like for example, Intel in this spiky neural network microchip called Loihi2, is to build a neuron which they have no choice. They have to make a circuit with using one accumulator, the neuron membrane potential to store the data, etc. That is big. It's big. So basically, they put a number of neurons and they multiplex. So this is also consuming more energy and more time. It's not ideal. So we need solutions. We need solutions. And that was the first approach that I have proposed to implement neural networks, were those large circuits. There is another trend, which is to use emerging devices, like, for example, memristors. One memristor is an electronic device with a metal insulator metal structure that can reach 2 or more states, resistive states, depending on the history of electrical impulses that we apply between the electrodes. Okay? They can have 2 stable states, 5 stable states, or they can have 1 stable state and 1 unstable state, which is used to do this spiking behavior. This is the field of research I've been working over the past 12 years, since I left Spain. And there have been several companies working in this type of devices, and these type of devices have 4 main applications. The neuromorphic computing, as I have mentioned, but this is still under development. They are now being commercialized as electronic memory for a few niche applications. And I say niche application because they can still not compete with state-of-the-art memories. Even the memristors fabricated from TSMC don't switch more than 100,000 times. So they cannot compete, for example, with NAND flash memory. So what is the problem of this? Is yield, variability, and reliability. We publish some scientific papers, we demonstrate some claims, we demonstrate the devices work, but when the company comes to fabricate and needs billions of devices that are all identical, still does not work. Okay? But this is a fantastic field of research. There are many exciting developments. Here I would like to show you 2 articles that we have published recently. The first one was in 2023 in Nature, where we develop microchips where we integrate 2-dimensional materials, using it as a switching layer in the memristors. And this other is also an article in Nature where we discuss the status of the memristor industry. This is a very exciting field of research, as I mentioned. But working in this field, I became a little bit eager. This is a little bit too long-term, and we want to do something that has a short-term impact. So we have been working recently in a new device called the neurosynaptic random access memory. And it is very exciting because this device is simply a MOSFET transistor. But what we have done is to bias it in a very unconventional way. What I have explained you before with this electrical field that produces the channel and then this other electrical field that drives charge, and this works as a switch, it is true. Here you can see, normally this terminal, the bulk, is grounded. We apply the electrical field here, and you can obtain these 2 figures of merit, the drain voltage versus the gate voltage, the drain voltage versus the drain voltage. These are the main 2 figures of merit. They are often called output and transfer characteristics, very popular among the community working in these devices. But the interesting idea, and something that we found that often is ignored in the books, is about this terminal. This terminal is always grounded. And the reason that you need to ground this terminal is because if you apply voltage that are relatively high, around here, and you measure this current, you observe a very large peak of current. This peak of current is something nobody talks about, but it's extremely important. I will explain you why. This peak of current happens because when there is current flowing between these 2 terminals, there are a lot of electrons moving in the silicon lattice, and then there are electrons that collide with the atoms, and they generate free electron-hole pairs. So what happens in this situation is that the electron flows in this direction and the holes flow in this direction. Now, what we have done is we disconnect this cable. If we disconnect this cable, what happens is that the holes accumulate here. And because this is a p-n junction, there is a diode. When this potential reaches 0.6 volts, this diode enters in action, and there is a sudden peak of current. Very abrupt and non-linear. Exactly what one neuron has to do. Exactly. It's exactly what I need. If I switch the voltage down, what happens is that this current reduces, and after some time, all these holes leak, and then I start in the initial position. The next ramp will start here. So basically, this is similar to a neuron, but it's a very, very slow neuron. In the next step, we put here a resistor of a lower value, and then what we obtain is actually a nonlinear transition with a hysteresis. This is actually what an electronic neuron has to do and what the CMOS circuit that I have shown at the beginning do. So this was quite surprising, and when we observed this, we tried to test it for several cycles. We observed this thing works pretty well. But in the next step, we want to see if this is reproducible in the whole wafer, in the whole silicon wafer. Unfortunately, we found no. This is a set of microchips that we got from our foundry, and we observed some microchips show this behavior, like this one here, and some microchips, like this one here, don't show this behavior. So this was a little bit annoying, but after thinking a little bit, basically what is happening here is that the doping of the wafer is not homogeneous. There is a gradient in the doping, and this makes that the microchip here has one bulk resistance and the one here has a different bulk resistance. So we connected a second transistor to adjust perfectly this resistance, and now they all switch at the same voltage, identical voltage. And they switch forever. They switch all the cycles that we have tested, they have switched well. Here I show you a few devices tested under two different biasing protocols. This is the first biasing protocol, and this is the second biasing protocol. As you can see, the ones that are tested under the same voltages, they show the same response. The variability from one cycle to another is small, and from one device to another is also small in both states. Just to put it in easy words, this is the thing I tried to find for more than 15 years with memristors, and nobody in the world found, yet we find it very easily in the cheapest and most compact device that exists, without any novel material, and is ready for going to circuit design. So this was something very surprising. This result, because it is so robust, is the reason that the editor of Nature accepted our publication. But that I show you is just the spike. The leaky integrate on fire mechanism is not demonstrated in that plot. This is what we demonstrate in this other plot. We apply pulses, electrical impulses, with different frequency, and when the frequency is low, we need some specific time to fire the neuron. When the frequency is higher, the time is reduced. And here we measure the firing time depending on the voltage of the spike, the duration of the spike, the frequency of the spike, the resistance of the bulk, and the gate voltage of the transistor. We have several knobs to adjust the performance of this electronic neuron, something that with the previous circuit that I show you is very difficult to do. You will need a much bigger circuit. So this performance was already fantastic for us, but we discovered two additional properties from this neurosynaptic random access memory cell. You remember this plot that I showed before when we want to do in-memory computing and we need some memory nodes that can reach several states linearly? Well, if you use, for example, memristors, where the change on the resistance is based on phase change on the material, or ferroelectric dipoles, or spin change, this is something very difficult to control. But with the MOSFET transistor, connected in this way, we manage to control this leakage of the holes very accurately and reach several states. Because this mechanism is a mechanism that tends to leak with the time, if we stop the biasing, we will reach this kind of forgetting characteristic. We lose the state. But this is something that it has to be like this to implement spiky neural networks. Finally, we also found that if the transistors are biased in a specific way, they can also trap charge in the gate dielectric. Basically, we are somehow building a floating gate memory, like a NAND flash memory, but without the need of the floating gate. And this is possible because the retention that we need to acquire for doing AI is much lower than the retention that we need to reach for memory applications. For example, if you take your USB and you store a picture, you want it to stay 10 years. This is the technology requirement. But for AI, for this storage of the nodes in the neural network, it's much lower. So maybe we don't need so good transistors to do that application. So we have observed we can reach several stable states. So this is a little bit the summary of the slides of the whole presentation, the device that we have created. It is an ideal building block to build spiky neural networks. What we are doing now, we have hired 3 circuit designers. We are trying to build the microchip, trying to compete with this one from Intel and with other spiky neural networks that have been reported using this new concept, which spares a lot of area and energy. So until here is the main idea that I wanted, the main take-home message that I want you to remember is that we have developed this NSRAM cell, and that it is very easy to extrapolate to the circuit level because there are no emerging materials, because the reliability is very high, and because the cost is very low. So we expect in the next couple of years, not only our group, but several others. In fact, a foundry in China already approaches to us, and a couple of circuits more. We are going to be probably launching a research center for this area in Singapore soon. Finally, I would like to thank my team of researchers at the National University of Singapore, especially this gentleman called Sebastián Pazos, who is one of the main responsibles of this device. If you are more interested on our work, you can check our most recent publications. And also, if you know anyone who is interested on working in this direction, either as a PhD student or postdoc or research fellow, you can apply for one of the job offers that we have posted in the Web of Talents. And that's everything I wanted to communicate, and I will be happy to take any question if you are interested.
Thank you, Mario. We have time for some questions, and we can do it in Catalan. It's fine for you?
Qualsevol idioma està bé.
Ok. Si tenim alguna pregunta del públic, podeu donar pas a alguna. Aquí. No, te pasarán el micro. Ara no sé on està el micro. Ok, l'han passat allà.
Sí. Hola. No sé si lo he entendido muy bien, pero aquí arriba estoy. Aquí.
Ah,
sí.
Perdona.
Si lo he entendido bien, o sea, se podría, o sea, no sé cómo explicarlo, no sé cómo preguntarlo realmente. ¿Cómo codificas los pesos, digamos? En una neural network, pues tienes los weights. Y yo supongo que estas neuronas, pues, se disparan cuando están codificadas a cierto voltaje. Es lo que creo que he entendido. ¿Cómo codificas esos weights en el chip? Y relacionado con la pregunta, ¿se puede hacer training en estos chips? O sea, ¿puedes hacer el update de...? Porque necesitas que estas neuronas cambien con el tiempo, ¿no? Tienes que hacer backpropagation y todo eso. ¿Cómo eso tipo, funciona en ese tipo de chips?
Gracias por la pregunta, es muy acertada. El tema del algoritmo del backpropagation es algo que se utiliza más para deep neural networks, las cuales funcionan con tensiones continuas. Un poco lo que estaba comentando en la slide en la que tenía el diagrama de la vector matrix multiplication. A ver, tienes dos tendencias. Una es hacer el entrenamiento del chip durante, digamos, el ajuste de los pesos, el entrenamiento en el chip, y también puedes hacer lo que se llama ex situ training, que es simplemente hacer el ajustado de los pesos externamente y luego grabar esos pesos en tu chip. Pero en nuestro caso estamos utilizando este método de computación asíncrono basado en spiking neural networks, así que es un poquito más diferente porque ahí nosotros ahora mismo nos estamos focalizando en el desarrollo de la red, pero basándonos en las neuronas. El elemento que estamos modificando es las neuronas. Los pesos son codificados en las sinapses, que también es otro melón que se podría abrir si hubiera tiempo, pero digamos que ese concepto que tú has dicho de los pesos es lo que tú grabas en las sinapses. Pero para Spiking Neural Network no es tan inmediato, requiere un cálculo un poco más avanzado que para la Deep Neural Network. No es algo tan inmediato como aplicar el Backpropagation Algorithm. No sé si eso responde a tu pregunta. Vale. Si te dan unos keywords, yo ya estoy contento. Gràcies.
Doncs moltes gràcies, Mario. En honor al temps hem de continuar.
Moltes gràcies.
Un fort aplaudiment per al nostre ponent.